Okay, happy Friday. Happy post-Perseverance landing safely on Mars Day. We're going to finish up the communications chapter by going over technologies, specifically hardware. So I thought we could start by looking at some block diagram of a sample spacecraft communications system. And we can walk through what kind of hardware is involved in transforming an input signal all the way to the output. So there was a block diagram last time that was talking about the modifications to a signal, but how do those modifications digitally happen on circuits? So we have circuits that are specifically dedicated to spectrum shaping or filtering. We have circuits that are dedicated to modulating, where there's an oscillator inside and some other kind of circuitry. We have power amplifiers. We have other spectrum shapers or filters. And then a node is a diplexer, or you can have a duplexer, multiplexer, simplex, some kind of plex technology that's connected to an antenna that ultimately transmits the signal. And the other way, if we were going to go in from the antenna, if the antenna was to receive some kind of signal, that diplexer would be on the receiving end. It would be passed to some receiver circuitry, some filtering or spectrum shaping. I don't remember what an AGC is, but then ultimately it would be received on this end by the onboard computer. Okay. So let's talk about the various technologies from that block diagram. Antennas are a huge portion of the technology space. So you can see there are a ton of different types of antennas, where we've got dipoles, which have subcategories in themselves. We've got a lot of aperture antenna types. And some of the antennas are depicted down here, where a helical antenna, hopefully it's clear why it's called the helical antenna. Horn antenna looks like so. And then these aperture type antennas, this one is a specific type called a parabolic reflector antenna. So we have a question here. Are most antennas directional because they are easier to develop and operate? And the answer to this is, for our specific application for point-to-point communications, directional antennas make a lot of sense. They're very power efficient in the direction that they're going. So you don't really need to have an omnidirectional antenna that broadcasts. For power-constrained applications or spacecraft like ours, directional is the most efficient. But then, why is it that most CubeSats, these 1Us, use dipole antennas? So as you can see here, let's just walk through what a dipole antenna is. So here is what the antenna actually looks like, where the axis that this antenna goes along is in this Z direction. The gain or radiation pattern of this antenna looks like so, where it looks pretty omnidirectional, especially in the azimuth plane. And then in the elevation plane, you see more of the two poles or dipole. So most antennas are directional, like deep space spacecraft are very directional when it's transmitting. It can be a little more omnidirectional when it's receiving. So why is it that the Artemis antenna is this omnidirectional antenna? So when it comes to CubeSat technology, it could be that the CubeSat doesn't have an ADCS or some kind of pointing control inside the satellite due to volume or power constraints. So it could be a better idea just to make it as simple as you can. So to do that, you want to incorporate an omnidirectional antenna. Make it simple, stupid is the phrase. And also a lot of CubeSats function in low Earth orbit. So when it comes to the signal that we're transmitting from a ground station to the spacecraft, when we're transmitting from the spacecraft to Earth, it can be a weaker signal, and we can just, in this way, an omnidirectional antenna can spray and pray that the signal gets from the satellite to ground. So it's kind of a design decision. Okay, and let's walk through other types of antennas. This is a parabolic antenna on a RainCube satellite. It's also a CubeSat, but it's larger and more capable. So here we see this parabolic dish. Its gain radiation pattern. You can see it's directional because there is this high gain along the bore site of the dish, and then lower gain at different angles. And you can see that depicted in this graph. Let's go to another one. Here's a patch antenna. You can also see a demonstration of that in a CubeSat. This actually has two different types of antennas. So this patch antenna, there's one at the bottom of the spacecraft, I would assume is transmitting towards Earth. And then there's this monopole antenna. And I would just assume that this is the transmitting and this is the receiving antenna. The patch antenna looks like so, where it's just a surface area, and its radiation pattern looks like so. It's some continuous combination of an omnidirectional and directional antenna, where there is some bias. You see, there is some directivity with its highest gain direction, but it does disperse a lot of signal in the other parts of the unit circle. And then here is what its elevation plane pattern looks like. So also kind of directional. Here is what a helical antenna looks like. And here's what its radiation pattern looks like. Very directional. All right, this one's pretty clever. I've tried to find examples of all of these antennas in CubeSat form. So here is a printed circuit board with a Yagi antenna embedded in its design. A Yagi antenna without all of that green stuff around it looks like so, where it's pretty much this very long stem with a lot of smaller prongs attached. It almost resembles a helical antenna in that kind of way. Its radiation pattern also kind of looks like a parabolic dish or a helical antenna radiation pattern, where you can see it's very directional. And then there are these smaller, just like higher order lobes of radiation coming off at the origin. Okay, here is a horn antenna. So you'll recognize this from the previous parabolic dish antenna. So there are two things that are happening. There is this parabolic dish, but there's also a horn that is doing that augmenting, amplifying the signal, where the gain radiation pattern from a horn antenna looks like so. It looks very directional. Okay, now let's talk about behind the antenna, there's going to be some transponder, transceiver, where a transponder or transceiver is a combination of some circuitry. It can be a combination of a simplex, duplex kind of technology combined with an amplifier. There can be multiple transponders and antennas on a spacecraft, as you probably have noticed from a previous picture, where different transponders and antennas can focus on different bands of frequencies. This can be because of your receiving is different from your transmitting. Okay, so a transponder or a transceiver can include some bands limiting device, such as an input bandpass filter, which I'll describe later on in lecture, some amplifier, a frequency translator, an output bandpass filter, and yet another power amplifier. So what is a diplexer or a multiplexer? Right, so a diplexer separates two different frequency bands in the receive path and combines them in the transmit path. These frequency bands usually will be wide apart in the frequency domain for the diplexer to work satisfactorily. It is often referred as RF power combiner divider with added functionality of filtering. Broadband filters are used to pass appropriate bands at telemetry, the TX and RX path, where T is transmit, R is receive. Multiplexer is the extension to more than two frequency bands. So you can see how the antennas are directly attached to the diplexer or multiplexer. It's kind of like the router or interpreter for the raw signal. Here you can see kind of like a schematic diagram of like a lower and a higher frequency being passed through an antenna. This is an antenna symbol. And then the diplexer separating out the low and the high frequency. So it does that filtering. It handles the toggling of the two frequencies. Another type of node that you can put right after the antenna is called a duplex, where a duplex is the use of a single antenna by both the transmitter and receiver parts of a single device or two devices. In other words, duplexer is a device which couples the transmitter and receiver to the antenna while producing isolation between transmitter and receiver. Both transmit and receive paths usually will have frequency bands very near, hence narrow band filters are used to separate these frequencies. So here I have a chart of the differences between a diplexer and a duplexer. Mostly I would say it's this difference where the separation of bands for a diplexer is very wide apart, and for a duplex, it's closer together. And this is just an image of some commercially available duplex system. Okay, so a lot of these systems will have power amplifiers, especially the transmit side. So the signal itself can be a very small powered signal going through electrical lines. But once you get to the antenna, it needs to be of a power that it can go through this whole distance of space and get to a ground station. So to do that, we have to amplify the signal. This is a circuit diagram of what a power amplifier could look like, where there are a bunch of capacitors and I think inductors that make up amplifiers. No, it might be, no, resistors and capacitors that make up amplifiers. The electrical engineers will recognize a lot of these shapes, but pretty much you have your RF signal coming in here. There's some external power source that will supply this amplification, but how do you insert that power while retaining the frequency and amplitude and phase of the original signal? So it goes through all this circuitry and eventually gets to the antenna where it actually emits that electromagnetic radiation. Here is just a depiction of what a power amplifier can look like. Okay. Another thing you'll see very commonly in communications circuitry are filters. So signals can have noise, and to get rid of that noise, you have to put a filter somewhere along the line. There are many different types of filters, such as bandpass, where you can specify the band of frequencies that you'd like to get through. A band stop, which is the opposite. You want to eliminate an undesired band. Low pass, where you can just have a cutoff and only allow signals at a higher frequency to pass. High pass, sorry, other way around. Low pass, you let lower frequencies. High pass, you let higher frequencies pass. And here's just a very simplified version of a low pass RF filter, where we've just got a series inductor and parallel capacitors offering that filtering capability. So that was a really short lecture. I'll take any questions. Let me stop the share.